When a battery is discharged, we may have different current voltage characteristics. The first one is shown here, voltage versus current density, and we would have constant voltage as the current density increases. And of course, this would be a so-called ideal discharge with negligible, with zero internal resistance. This is a highly ideal situation. You want your battery to of the usable voltage go towards the external circuit to drive the external electrical devices or component. And this only happens when your internal resistance is negligible, it's zero. Okay, so we call this ideal discharge. In reality, we may come across the voltage current density characteristics, something like this. The vertical axis, voltage, the horizontal axis, current density. And when it is zero current density, the voltage, the cell voltage is the highest open circuit voltage. And if there's no internal shorting, it will just be the equilibrium potential. And then as the current density increases, the cell voltage, terminal voltage starts to decrease, maybe initially quickly and then gradually, linear fashion, and at the end decrease sharply again. Okay, and this would be the typical discharge curve with both activation and mass transfer limitation. And activation at the beginning, mass transfer limitation at the end, and in between is linear that represent omega loss. And finally, we may have a different scenario that we have the voltage more or less flat, and towards the end it drops off suddenly. This would be the discharge with fast electrode kinetics and also low ohmic resistance, but great mass transfer limitation. Okay, but most of the voltage characteristic looks something like the one in the middle. Okay, and for this case, if we draw a parallel line parallel to the horizontal axis that represent the open circuit voltage or equilibrium potential, and then there will be the potential drop at a given current density. There will be the potential drop from the equilibrium or open circuit cell voltage to the actual cell voltage. That is what we call voltage loss or voltage drop. And this for galvanic cell, that will be equilibrium potential minus the actual cell potential. That's what we learned before in chapter 3. And then equilibrium, this voltage drop is between equilibrium, the parallel line, versus actual. This is the solid red line. Okay, and then from what we learned before, this voltage drop would just be the current times the in cell internal resistance, this battery internal resistance. And then if we examine the internal loss mechanism, we would have different contribution. The first term would be I R ohm. R ohm represent ohmic resistance. That represent the voltage loss due to the ohmic resistance related voltage drop, and that quite often mostly come from the electrolyte ohmic resistance loss because it's an ionic conductor. And then we would have three terms. I use absolute value. Eta anode, that represents the anode activation over potential. Eta cathode, that represent the cathode activation over potential. And eta concentration, that represent the mass transfer over potential. So the voltage loss, quite often we can write it as four-part contribution. Ohmic loss, anode electrode process, cathode electrode process, and mass transfer, quite often diffusion related limitation over potential. Okay, so these are the different battery discharge voltage current characteristics and the voltage loss for a typical battery and the origins of the source for the voltage loss.